Welcome to my Texas workshop. I'm Randy Lammers.
I'm Aaron Keevan.
This is Würth Knowing.
Würth is the world's largest fastener company, and one of the questions we most often get to our employees and myself as an applications engineer is, what torque should I use?
Yeah, Aaron, unfortunately, that is a question we get way too often. Anyone that asks that question truly doesn't understand what torque is, otherwise they wouldn't have asked the question. Companies call their fastener distributor and they ask them to look up in a chart or somewhere in a book what torque they should use for a given fastener that they've purchased. And that's really incorrect because the torque really is overcoming friction and we don't know what the joint friction is. But I tell you what, let's do this. Let's go back to bolted joint 101. Why do they have a fastener to begin with? And let's take a look at that. You take two pieces of material. What we want to do is we want these two pieces of material to be put together and we want them to stay together. So let's do this. Stay there. Okay, that didn't stay. Aaron, why won't this stay there?
Well, you don't have a fastener to hold it together.
Correct, but why do I need a fastener?
Well, it won't be held together, won't be clamped.
Okay, well then why do I need a clamp? Well, the answer to the question is because I have an external force. The external force in this situation, we call it gravity. The external forces are taking these two pieces and making them come apart. Now, what if I do this? What if I take that piece of material and I set this piece of material there and I use that gravity to my advantage? Now look at what's happening, Aaron. They're staying together.
But how do you overcome that?
Okay. So we have a fan that created another force, a force that was unpredictable. And that happens a lot in joint applications. So understanding what your product is, how it's being used in service is absolutely critical to bolted joint design. So let's do this. So we have external forces. I've understood my external forces, and then I grab this. What is that, Aaron?
I'm pretty sure that's a paper clip, Randy.
Well, it's a paper clip, but it's also a fastener. And so if I put that paper clip or put that fastener on there, what does that paper clip do?
Holds two pieces of paper together, Randy.
It creates a clamp load. That's why we have a fastener, is to create a clamp load. So look at this. As long as that fastener exceeds the external load, so here I just have a static load and it's exceeding it. And as long as it does that, it'll stay together. But in assembly or in application, I get this motion. I get vibration, I get extra pull. Now it came apart. I didn't design or didn't anticipate the other external forces. So that's what happens. So understanding the clamp load needed, the external loads, that's what it's all about. That's why we have fasteners.
So that's a really good explanation of the external loads. But some of the other things I know we have to worry about are joint relaxation, joint creep, thermal expansion and contraction. Those can also cause joint loosening.
Exactly. So the environment that your product's going to be in, that's also understanding that, because they do come loose just because of that. So understanding, let's say, what size fastener I want, how many fasteners do I want, what's the strength of the fastener, all of that is critical in understanding your joint. If you do that first, then you'll create the best joints to stay together forever.
So why do fasteners fail?
Okay, why do fasteners fail? Oh my gosh, let me tell you about my Uncle Mo. I have an uncle out in West Texas that has been a rancher and a farmer. He farms a couple of sections of land and he's gone through a ton of agricultural equipment, and I have been in the fastener business for 46 years. And Mo has told me exactly why fasteners fail, because he breaks them all the time. You want to know why fasteners fail?
Okay, sure, I'll bite. Why?
Because I'm out there selling cheap-made bolts made out of cheap-made steel, and by golly, they just don't make them like they used to. Well, Uncle Mo, that's not exactly right. It's because he doesn't understand the frictional forces. Now, you can imagine, Mo's about 5'8", and 125 pounds soaking wet.
And I'm guessing that he probably had a special tool to install these bolts.
Of course he does. He goes to the barn and he pulls out this, his cheater bar. Now, if you can imagine this, take a 125-pound small man out there on the end of this bar, and he puts everything he has into it. As you can imagine, he's got a lot of torque and a lot of load, and he's breaking bolts. And he's calling me up and going, Randy, you're out there selling those cheap-made bolts again. They don't make them like they used to. Well, Mo, I've tried to tell him it's all about the frictional forces. And you're also, put your cheater bar down, that's way too much load. But how much grease have you put on that joint? How much dirt is in that joint? How rusted is that joint? That changes everything, Aaron.
Sure. And so I know that when I tour customer facilities, we see this a lot too. They're using impact wrenches. And you know, they take that mentality that when it's tight, it's probably right.
So tight is right, or tight enough is good enough. I get that all the time. And we have a lot of customers using impact tools, and that's okay. The torque control, by the way, on an impact tool is knowing when to let go of the trigger.
Sure.
And so we get that, but that's okay. There's a lot of joints that's fine for. Those aren't the joints we're talking about. The ones we're talking about are where it's safety critical, or where we know, based on the product I'm making, this joint must stay together in its application. So I have to create a proper clamping load so that the joint will always stay together. Those are the joints that we're talking about.
Sure, and I think the best way to actually explain that is to actually do some demonstration. And we've got a setup over here I'd like to show you, Randy.
Sure. All right, let's take a look. What do we have here, Aaron?
All right, Randy, just like any good experiment, we have to make sure that we have the proper personal protection equipment. So I brought our safety glasses today, and I'll explain what we have in front of us. What we have here, Randy, is we have a load cell. This is gonna tell us how much tension is in the bolt,
Okay.
and it shows us pounds force right here on this gauge.
Okay, so we use the torque wrench for torque, and we use the gauge or the load cell to create the load.
Correct.
So Aaron, I've looked up the Industrial Fastener Institute catalog on torque. And so based on the frictional forces of laboratory test results, it says for a 5/16/18 by 2.5, which is what we have, grade 5, zinc plated, trivalent chromate, that you use 249 inch-pounds of torque to accomplish 3,600 pounds of load. So let's run some tests at 249. Let's see what our load is. So let's see, to set this up, we're going to put our cap screw through, and we do need a hardened washer to go against our load cell to begin with. So we'll put that on there. We'll put the flat washer on there. That's just a regular soft USS flat washer. And then let me rotate that nut. And so you might want to go ahead and take that snug, and let's see what happens.
All right.
So go ahead and rotate that here, and let's see what we have.
I'll make sure to turn this on, make sure we're at 249 and set, make sure we're zeroed out, and looks like we are. So I'll give it a little snug test first before we go to full torque. All right, that's pretty snug right there.
Okay.
All right, so looks like I can start off at 0 here. And I'll go ahead and get this set on the load cell and start to tighten the nut.
All right, let's see what kind of load we end up with.
I'm gonna look for this to turn green here, Randy, and that'll give us an indication whether or not we've met.
Okay, 249. And it looks like we're right at 32, 34. We're exactly at 3,600. So let's write that down. So test number 1, we received 3,600 pounds of load. And let's loosen that up. Let's put another one on. Let me grab a flat washer and a hex nut. You loosen that up, we'll put another one on. Now we always want to use fresh hardware when we're doing tests like this. When you do load one up like that, you're burnishing the threads a little bit, so we always want to use fresh hardware. This is out of the same lot, so I want to make sure everyone understands that. This is the same manufacturer's lot number and plating number of both the hex head cap screw, the hex nut, and the flat washer. So we're not making any lot number changes. So should you go out in your bin and pick up nuts and bolts to do your assemblies, this would be the same lot numbers you would typically pick out. So, okay, let's go ahead and run Run one more.
Almost got us set up here, Randy. Just give me a sec.
All right, let's get that flat washer on there, and I'll rotate that nut. Let's get that just snug enough to where we have a beginning of a needle movement, and then run the 240 inch-pounds, and we'll see what load we come up with.
Sure thing. I'm gonna set this back up. Got it on Tighten now. Got to take a look at this as I'm.
All right, get the 249. Okay, we're right at 3,200 pounds. So test number 2 is 3,200 pounds. Let's do a third one, and let's just see what kind of variables that we're going to end up with. Go ahead and loosen that up, and I'll quickly get this put on there for you. So let me put the flat washer on there. Here is the hex nut, and tighten that up. Let's see what we feel here.
Let's see if we get here to 249. Again, it's giving me a green.
Okay, this time, oh my, Aaron, this frictional force was completely different. We're at, I'm going to call this 2,100 pounds. So that would be test number 3. Now, that's 2,100 pounds. In conclusion, Aaron, with 3,600 pounds of force for our first test, down to 2,100 pounds of force for our third test, that's a 32% variance. That's not unlike what we typically teach for zinc-plated fasteners. We typically talk about 35% variance, and this falls right in line with that. So what we know is we know that 40% of the torque is to overcome the frictional forces on the threaded section. 50% of the torque is to overcome the frictional forces on the bearing surfaces. In this case, that's the nut rotating against the flat washer.
Wow, so that means we're only taking 10% of the force that we're applying through torque to actually go into the clamp load of the assembly.
That is absolutely correct. And that is why we tell customers all the time, please be very, very cautious about ever using any torque that you get out of a chart, an internet search, or someone gave you that torque, because that does not pertain to your application, to the frictional forces of all of the materials in your assembly. It's completely different. Think about this. What if I paint my surface? I decide then I'm going to paint first, then assemble. Paint can act as a lubricant, but it can also act by giving more friction, actually as it reacts with the surface of the fastener.
Yep, same thing with the surface texture of an assembly. So you had one that was machined with a nice clean machine finish to it, and the next time it was machined, came in with a rougher texture, that bearing surface changed. That changes the frictional factor right there.
Exactly. Rust preventatives are another thing that happen to us all the time. So maybe this time the material comes in, it has just a oil sheen on it that's a little bit different than it was before. Different frictional factors.
Thread lockers is another one I can think of. Your pre-applieds and your liquids. With your liquids, they act as a lubricant initially, but over time, and they harden, they actually will work against you in friction. And then with the pre-applied thread lockers, you have a prevailing torque element, and that adds an additional amount of friction.
It does. You know, I have customers that will take the same fastener, the same bolt, and they'll use it in this application over here, and they'll use it in this application over here. It's the same fastener. So, because of different frictional factors, they have to use different torque to achieve the clamp loads that they're looking for. So, if anything changes in the frictional factors of the components that you're assembling, if anything changes in the friction, so does the torque to tension relationship. Torque is a rotational force to overcome friction, and that's definitely worth knowing.
If you like what you saw today, hit that subscribe button and the bell icon, and we'll see you next time.